So, ladies and gentlemen, welcome. This is the third time I've done this. I'm getting a little irritated. I have not been able to successfully record this and keep it going here, so I've seemed to have lost it every time I've done it. So I'm going to try one more time. I'm going to talk a little quicker because I'm getting bored of this at this point. Chapter 9 is all about area and perimeter. So, as many of you already know, well, let me back up 1 second. You are welcome to stop this, rewind it, replay it. If you don't want to listen to what I have to say, you could mute my voice here and just look at what's going on. But you are expected to achieve the same goals, produce the same results. Take notes, write down things that you see are up here, attempt all of these problems, show work for all these problems, and hopefully get the same answers I get and understand where they came from. So perimeter is the distance around an object, or the length around an object. You can call it either one. If you're trying to calculate it, you find it by adding up all the sides or finding the sum of the sides. So I don't care whether you call it distance or length around an object, either one would work for those, as opposed to area, which is the stuff inside or the space inside a figure. So on your paper, try to grid this little rectangle up into a 3 by 2 rectangle, so you can actually see that it's space, or literally the number of squares that fit inside a shape. It is square units, but it's actually squares. It's 1 by 1 squares. So you can see that there are 6 squares that are fitting inside there. And of course, all of you know that comes from 3 by 2, length times width, for area of a square, or area of a rectangle, sorry. Perimeter, you can quickly calculate that. Would be adding 3 plus 2 plus 3 plus 2. Perimeter is 10. So we're going to do a lot of calculating area and perimeter throughout this chapter. A little detail I want to go through here. The little variable lowercase b, you probably can guess what that stands for. It stands for base. And the key concept in this little part of your notes here is that any side of a parallelogram or a triangle can be called the base. And I intentionally oriented this, kind of turned it sideways here, so you don't think the base is the bottom. The base does not have to be the bottom. You might have to turn your paper all the way around to do a problem, and the base might be the top. Base might be the left or the right or a diagonal side. The key thing is how it relates to the height. The height, I'm going to sketch it on here as you did a lot in chapter 8 with trigonometry. The height is this altitude, is the fancy word for it if you remember, is, you can see on your paper, it's probably related to this base. It's perpendicular. It's always at a right angle with the base, which means a lot of trigonometry will apply, a lot of Pythagorean theorem will apply. You'll see I'm not going to give you too many easy problems where it's just length times width or base times height. You're going to have to do more than just that. So it's always perpendicular with the base. Height and base are always perpendicular. Base is usually a side. Height is usually often not a side. It's often a part inside the actual figure. And the same thing with parallelograms. I'm going to call this little b. Don't get confused and think this is the height. It's a slanted value. I'm calling it S for side length. In this case, it's not the actual height, with the actual height being an altitude inside the figure in this case. And of course, you could draw that altitude out here as well, or out here. So, let's derive or refresh a formula in your brain here. That first one, you can call it a rectangle. You don't have to draw the right angle boxes on there, but I just threw a couple of them up there to remind you. As you all know, of course, we're talking about base and height. Area of a rectangle is base times height. You may have been used to calling it as length times width, and there's nothing wrong with that. Length times width is fine, but we're going to get a little more detailed. We don't want it to be length and width because those are always sides, or those are usually sides. Height is not necessarily a side. So I'm going to go down to this example before I moved on to the parallelogram and the triangle. Give you the diagonal is 13 feet. And this is a rectangle. You can make the assumptions with this being a rectangle and having right angles. The base is 12 feet. I'm not going to give you the height. That's where you get to work. And you're trying to use this formula, base times height, but you only have one of the variables. How do you find that other one? And you're certainly thinking Pythagorean theorem. The height squared plus 12 squared equals 13 squared. So you're thinking about doing some Pythagorean theorem here, applying Pythagorean theorem, maybe applying trig in this chapter a lot. I believe you run those calculations, subtract the 144, height ends up being 5. And of course, then you can just do 5 times 12. You can get a space of 60 square feet, or 60 feet squared. You can see the notation I'm using on that as an exponent. All right, simple enough. Rectangle example, applying some Pythagorean theorem. Go to the middle of your page. You've got a parallelogram there. And it's interesting that this formula is exactly the same as this one. But these shapes don't look the same, which might throw you off at first. You go, how can it be base times height if the shapes are not the same? Well, base is still a base. You know, you can call that the same thing. If you think of the altitude again, maybe sketch this altitude on your paper. Think of how this triangle, if I were to cut it off, literally scissors, cut it off, and move it over here, it would fill in this little space. Think about what shape you'd have if you cut that off and you filled it in on the gap on the left. You'd have this shape. You'd have a rectangle. So it kind of makes sense that that formula would work base times height, with again height being an altitude, not this slanted side length over here. The more you slant it down, it might be logical, the more you slant it down, the smaller that area would get. So I'll give you an example to try with that one. I give you a 37-degree angle, give you the base of 24 meters, and I'm going to give you another side length, 10 meters. I want you to try to find the area of that parallelogram.